Hey guys, I want to make a quick video for you. I got to thinking about this a little bit, and we're going to be using meters and amp clamps and things like that as part of this class. And I typically have a lesson dedicated solely to meters and instrumentation and things like that. But I've decided to sort of integrate the meter part of it from the very get-go, okay? So we've covered lesson 1 in the very fundamentals of AC and DC electricity. But what I thought I might do is just make a real quick video that incorporates some live demonstrations on using the meter with me showing it how it's used. So I want to kind of cover some very basics that we sort of touched on already, and we'll go a little bit more in depth and give you some of those live demonstration videos and get you set up so that when you come to lab and you get your hands on the meter, it goes a little bit better and it'll give you a better understanding of the meter. So we're going to talk about the voltage, current, and resistance, multimeters, and amp clamps. We've already covered those as in general terms, but I want to talk first of all about our multimeter when we're reading voltage, okay? So we got a circuit set up here, and you should all know that this is AC voltage. This is something in our home or our business or our brewery, and this is a very fundamental schematic here, but we have our conductors, and I've taken the load out on purpose for right now, and we have a return back to our neutral that will complete our circuit should we have a load. Now there's a new symbol here, and this is the ground, okay? And the neutral side of our circuit is grounded, okay? And we're going to go into what that means a little bit later, but I want to show you that. For right now, just go ahead and let you introduce you to the new symbol of ground, okay? So when we measure something with our voltmeter, what we are measuring, I think I covered this earlier, but what we're measuring is the difference in potential from one side of the power source back to the neutral or the ground. Now in AC, we're talking neutral and ground. In DC, with like a power supply or a battery, we're talking about the negative terminal, okay? Versus as opposed to the positive terminal. But let's stick with AC for right now, okay? So we've got 120 volts coming out of our conductor, and we have a neutral going back with no voltage at all, okay? So what the meter is actually measuring is the difference in potential from one side to the other. Now it's an open circuit, so our 120 volts travels through our conductor and stops right there because it has nowhere else to go. So we put 1 lead of our meter, and we're set on volts, and we're going to get all that in the lab, but we set it on volts so that it measures volts AC for us, not DC. And we put our meter lead right up there, and then we reference it to the neutral on the other side, and the difference from one side to the other is 120 volts. That's why it reads 120, and it tells us we've got a 120 volt power supply, okay? Now, if we were to take that meter and move it over and measure from this side on this part of the conductor, and we had a measuring point right there, this conductor, there's no potential difference because the 120 stops right there, and there's zero, there's nothing on the neutral side, okay, or the grounded side. So we got 0 here and 0 here, and there's no potential difference there at all. They're both 0, so the difference between 0 and 0 is 0. That's what it measures, okay? Likewise, if we put that on the hot side, we still have 120 volts coming right here. It's going to pass on this conductor, and when we measure our voltage at these two places of the conductor, here's 120 volts, here's 120 volts. There's no difference in potential. So even though you're on a 120 volt wire, a hot wire, a live wire, your meter's still going to read 0 because you're not referencing back to the neutral, the grounded neutral as your reference point. So there's no difference in potential, okay? Remember, potential is basically the voltage, the power available to us, okay? So there's no difference here, all right? Now, using a little household example, and I always like to tie these together, okay? So we have an outlet, okay, typical of your house. I've got it turned upside down so I can get my graphic in here just right. But we've got the 120 volts connected to this terminal, which will then travel from there to this slot right there. And that's the slot for our hot wire, our lead. Our 120 volts will come out of that. And then we plug whatever it is in. Like I used a vacuum cleaner last time, and it would be a light bulb. So it goes through the filament of the light bulb, comes back to our neutral, and then it comes to here where we have our neutral connected, and we go back to our neutral side of our power supply. And here's a ground screw, a ground terminal that takes that grounds our outlet back to our panel with a ground wire, and that's for safety purposes, and you'll see that in just a second. But what we're doing is one of the lab activities we'll do is actually plug our meter, or connect our meter into a live socket, and we'll be measuring the difference in potential from this side to this side because there's nothing coming out here and connecting it to here as it sits. So we'll measure it And the difference in potential from here to here is 120 volts. So our meter is going to read 120 volts. Now, that was just an example, but here's one with a heating element that we're using. Okay, this is a heating element for a hot liquor tank, mash tun, boil kettle, doesn't matter. And this is just a very simple schematic, okay? And so we've got 120 volts applied to this. And then when you want to test to see, first of all, when you are checking to do some troubleshooting, once you're sure you've got power coming out of our power source, you've got 120 volts AC in this example, we know we've got that coming out of there. We want to check and say, okay, if the heating element's not working, why is that? Well, first thing you got to have is power, okay? So we're going to check power coming in, and we're going to reference it to the neutral side, okay? So even though it's connected to the heating element, we're still going to be able to touch these terminals right there on the heating element and determine whether or not we've got power coming to the heating element, okay? So that's how you would actually use it in a real world example, okay? Now, here's where the ground comes into play, all right? Now, let's suppose that we've got power coming through here, we've got a good element. The element runs this electron flow in and out and comes back out here, and it's seeking the neutral, okay? It wants to get back home like we talked about earlier. It wants to get back home, but let's suppose we had a break in our neutral conductor. All of a sudden, we've got on this side a live wire. We've got a live 120 volts swinging in the air, okay? So we got 120 volts coming out of here, coming out, and it's looking to get back home, but there's a broken conductor, so we got a live conductor. So what happens is, if this live conductor comes in contact with our mash tun, our boil kettle, hot liquor tank, whatever the equipment is, if it comes into contact with it, this becomes energized, it becomes hot. So now we've got 120 volts on this stainless steel vessel, and it's basically a stainless steel conductor. So someone walks up to it, we're standing on the ground, okay, and there's our ground connection. Suddenly, instead of this going back to our neutral, our body becomes the connection between the vessel and the ground. We become a ground conductor, we become a conductor, and the voltage can pass through us. And my point is that you can come up there and get shocked, electrocuted, and it becomes dangerous. It's hot. So what we do is, that's why we ground our equipment, okay? The equipment should be grounded so that in the event that a live wire does, if our neutral, for example, breaks and we've got hot wire touching our vessel, it will immediately, just like that, ground it, it will literally take the current to a ground rod in the ground, that's why we call it a ground, and it will dispense of it there into the ground, and it will run it very quickly because of the current flow, the breaker or fuse, whatever our protection device is, should trip or burn through. But that's the purpose of the ground, is to keep you protected so that you can walk up and not get shot. Sometimes the ground between your shoes kind of insulates it a little bit. In best case scenario, you get a good shock, and that's about it. But if the ground in your shoes is good, and the current can flow through you to the ground, that's where it's going to go. It's going to go through the path of least resistance, okay? So that is why we ground our equipment, and that's the purpose of the ground, okay? This also applies to DC voltage in terms of how we read with the meter, okay? Now, what I'm saying, what applies to DC is in terms of how we read the potential difference between the positive and the negative of our power supply or our battery. Again, we don't use batteries a whole lot in brewing, but there are power supplies for the controls. So if you have to measure to see if you have DC voltage coming out, you've got to measure between the positive and the negative and see if there's a potential difference. But that's what we're doing when we actually plug a meter into the outlet, or when we're touching it to a heating element or a control relay or something like that, and it gives you an idea of what the potential difference is, and that's what you're reading on the meter. So take a look at this very short demo on how we actually, the meter showing the actual results of measuring some voltage in an outlet. Okay, and when you get through watching that, stay tuned because there's going to be more. So guys, right now I'm standing in front of the disconnect for the control panel for a brew house. It's being fed by 208 volts from our system, and we are feeding it down to the tops of these green fuses that you see. This is just going to be a real quick demonstration on how to measure the voltage for those who have never used a meter before. So I'm in the off position here, and we're going to measure voltage AC. You see the little sine wave, so we know that the V is for voltage and the sine wave is for measuring AC. So just very quickly, we're going to take our leads and very carefully touch the tops of the fuse blades, and you can see we're reading about 211 volts. Now, it's a 208 volt system, but it's going to read, there's going to be some variation. Hopefully nothing less than 208 volts, but it could get up to 212, 213. But that is typically the result of how much load is being pulled or not pulled on the transformers from the utility company at that moment. The higher demand, peak times, you'll see that voltage drop, but not below 208. But then usually when there's not a lot of activity in the building, the voltage will rise up just a little bit. But we still consider that a 208 volt system. So I'm going phase to phase, and you're going to learn a lot more about phase to phase voltage. And we have a 208 in our system, okay? And we can take one of those legs and we can measure it to ground, or neutral, excuse me, and we wind up with 120 volts, okay? Likewise, I can go to the other fuse here. I can go down here to the ground terminal, if you can see that on the video, okay? And you can measure 120 volts there because, like we said, our neutral is tied to ground. They're kind of the one and the same. Now, if I go to measure voltage between ground and neutral, remember the voltmeter measures the difference in potential. We got 0.0 and just a little bit of stray, very, very small voltage. It amounts to nothing. So we consider that 0. So the neutral to ground should measure 0 because there is no potential difference between the neutral and the ground side. So if we go to our hot side, which is the voltage coming out of our panel, and we reference it to neutral or ground, which is sort of the same thing. When we get into troubleshooting, you'll see where the differences are, but this demonstration is just to show you what it's like to measure phase-to-phase voltage and then phase-to-ground voltage. So just a quick demo, and we'll move over from here. Okay, so now you've seen how to connect a voltmeter and what it actually reads. Okay, the next thing we're going to use as part of our multimeter, voltage is just one of the things that it can do for us. The next thing we're going to talk about is its ability to read resistance or continuity. Okay, same meter, okay, same leads and everything, just we're going to move the dial over to the little the Greek omega or the horseshoe sign, okay, to measure ohms, okay? So the first thing we would do is we would turn it over away from our volt setting and slide it over to the ohms with our dial. But you typically measure resistance or continuity for things such as heating elements, like I've shown you in the previous video, control relay coils, the coils that bring control relays in and out, okay? Fuses that might be blown to test if is it a good fuse, bad fuse, trying to find out where a voltage is missing. Also broken conductors or circuits. The ohm meter or the continuity meter can be used to test for those things there, okay? And the way we do that is we've got a couple of rules, okay? But first of all, we've got 3 heating elements in this circuit. Now, I want to tell you right now, you'll never see this, okay? You'll never see 3 heating elements wired in series because of voltage drop. Something we'll get into a little bit later as far as distribution. But you got 120 volts, and this is just to demonstrate the resistance reading of the ohm meter, okay? So we've got the 3 elements wired in series, okay? Volts come out, go in and out, and back to neutral, or ground to neutral. We already talked about that. Okay, so there are a couple of rules that you have to follow when you're using the ohm meter section of your multimeter. Okay, rule number 1 is you have to isolate the circuit from the power source. You cannot measure resistance on the ohm setting while there's still power on the circuit. Okay, it could mess up your meter. At the best case scenario is it doesn't mess up the meter, but it gives you some really, really bad readings you won't be able to make sense of because it's probably jumping around. But rule number 1 is isolate the circuit from the power source. Okay, now after you've done that, rule number 2 is isolate the component that's being tested. And here's why. Okay, if you were to take your meter, okay, and you've isolated your power, okay, and you take your meter, you set it to ohms, and you know you got 3 elements that you're measuring, and you put your lead right here at the incoming power, and then the outgoing back to neutral lead there, okay, that conductor. you're going to measure the resistance of all three of these that are in series, all right? So if this one's supposed to measure 10 ohms and they're all identical, you're going to wind up with a reading of 30 ohms, okay? That's not how you do good troubleshooting. You want to isolate the component down to the component level to figure out which one's bad of these three, okay? So what you do is you need to isolate the component. Disconnect the wires completely from, or the plug, depending on how it's wired, okay? But you want to disconnect that power source like that, and then just test the element itself, okay? So you're basically going to send a small voltage through this heating element, and hopefully it returns. If it's a good element, there will be continuity, and it will return with a resistance value, because the heating element itself is going to give the resistance to that electron flow. It's going to heat up, which is the whole purpose behind the heating element. So we're going to have that, we're going to see if there's a complete path from this terminal to this one, and it has to go through the element back out to this one. So that's how we measure the resistance, and we have to, number one, isolate the power source, and then we have to isolate the component. That's it in a nutshell, the general rules they have to follow as far as measuring resistance or continuity. Now take a look at this video and see how it's done with the actual meter. Okay guys, so one more demonstration with the multimeter, and that is reading the resistance. And we're going to use a heating element out of the boil kettle. And what we're going to do is we're going to connect our leads. And first of all, we're making sure that our dial on our multimeter is set to the horseshoe or the ohms or the omega symbol on the meter. Now, remember, we have to isolate from the power source, and we also have to isolate this from all of the other loads that are on that circuit. So I've got this element out standing alone. So what we're going to do is we're going to put our leads and the terminals here on the element itself. And as you can see, it's reading about 9.9 or 10 ohms of resistance. That's how much resistance that this element is going to provide or create in the circuit. So now what I want to tell you here is this one is the ground, okay? And remember, we don't want hot leads going over to ground, but in the event they do, this ground is there to protect us. And you'll notice there's no continuity between the hot lead and the ground, because this is good. This is a good element. It's not grounded inside. And we can take this one over here and check to make sure that there's no grounding going on this side either. Now, one thing you do want to make sure of is when you're reading something, don't use your hands up here with this, because what will happen is the meter will actually read through your body, and it will distort the reading, okay? So what we can do is we hold this meter here, and I'm just holding it in my hands. You can see the meter start to dance around in mega ohms, okay? Because it's actually reading resistance through my body. My body is made up a lot of water, okay? And as a result, water is a conductor, and is not a real good conductor through my body, but water is a conductor. So you can see it's getting a reading there on the multimeter just by me touching the two leads. So with that said, you're going to always make sure you're isolated, and make sure you don't touch the leads. It's not going to hurt you or anything like that, but we just want to make sure we get good, accurate, solid, steady readings on our display. But that's just a quick, this is a quick real world resistance reading I wanted to take for you and show you on the video. Thanks for watching, and jump back into the other videos. Thank you. Okay, finally we're talking about amperage, all right? We've talked about voltage and resistance. So those are the two things that we can measure with our multimeter. We can also measure one more thing, and that's current or amperage, okay? Now, when we use it, the current, not every meter will be able to take two. Okay, we're back, and we have so far covered with our multimeter the voltage readings and also the resistance or continuity readings with our multimeter, depending on how we've got the dial set, okay? And what our circuit, what we're trying to read in our circuit. Finally, we come to current reading. Now, I will tell you that not every meter can measure current. It just depends on what kind of meter you buy and its capability or functions on it. Okay, this one here has the ability to read AC and DC amps and milliamps, okay? But not every meter has that. Some of the entry-level fluke meters just measure voltage and resistance or continuity. That kind of is a good thing, and here's why, okay? Reading current with a multimeter is a little bit troublesome in what you have to do to get it to be able to read, and also it's not really cut out for anything very high, and I'll go through that. So really, a multimeter, probably not your best bet to practically measure the current flow in a circuit. And again, that's for practical purposes, all right? Instead, we want to use the amp clamp, but let's take a look at this and what we're talking about as to why we're not going to use that very often. So we got our circuit here like we've seen before. We got our power source and our heating element, okay, and everything is all is right with the world, okay? So, got a couple of rules that you got to follow as far as the amp clamp goes, all right? Number one is the meter must be in series with the circuit. What do we mean by that? It's got to be part of the circuit, okay? So, number one, the circuit must be opened. We have to literally open the circuit somewhere. We got to kill the power source first. Then we have to open the circuit, undo some conductors and disconnect some conductors, and then connect our lead from our meter to the hot conductor, pass the current through our meter, into our meter, out of our meter, and on through the rest of the circuit. So in other words, our meter is now part of this circuit, okay? Because think of it like this, okay? Remember we were talking about water molecules as far as the current in the water analogy, okay? When you're measuring current, you want to measure every one of the electrons that are flowing through there. If you send some of them this way and some of them this way, you won't get an accurate reading and it won't read properly. So all of the current flow, or like we're talking water molecules, they got to flow all through this meter. Like the water meter at your home, okay? The county doesn't route it halfway around the meter and give you free water. Every water molecule you use goes to that meter so they can charge you for it, all right? Well, sort of the same thing here in that all of the electrons have to flow through the meter. So, like I said, our rule is, number one, is the circuit has to be open and the meter has to be part of the circuit, okay? Number two, it's got to be in series, so it's in series with the circuit, as I said, okay? Now, here's why we don't typically use a multimeter to measure current, because it's got a 10 amp fuse rating on most of your meters, okay? So anything greater than 10 amps is going to blow the fuse in your meter, and those meter fuses are very expensive, okay? In fact, it's probably about 70% of the cost of the meter. Those fuses are very expensive. So you don't want to blow them, okay? But they're there to protect the meter in the event that they do get too much current. So we don't want to have to, number one, go through the hassle of breaking open a circuit and then run the risk of running something, our current through our meter at the risk of blowing our fuse, okay? The other thing is that, we'll get into this in future lessons, you have what's called inrush current, particularly with electric motors. As soon as they become energized, the split second they become energized, the amount of current to get that rotor to spin is very high, 6 to 8 times the motor's rated load amperage, okay? So it spikes very, very quickly and comes right back down. I mean, we're talking like milliseconds, it spikes. But that spike could be well over 10 amps. For example, your motor or whatever may be rated at, say, 5 amps. But your spike, your inrush current could be 5 to 6 times that much. So you're looking at 25, 30 amps. And these fuses are going to blow very, very quickly, very quickly. So it's not going to be able to compensate or ride out that inrush current, so you're going to blow your fuses in your multimeter. That's why it's not a good idea to measure current in a circuit with a multimeter. So it's always good to follow rule number 4, and that's use an amp clamp, okay? It's a lot better. And again, we clamp our amp clamp around the conductor carrying the current, because that current creates a magnetic field around the conductor. As the current's flowing through it, it's creating a magnetic field around it, and that magnetic field is being induced in this, it's sort of like a little small transformer, but it's being induced in this coil that is making its way around the conductor, and that coil then, through the electrons here, gives us a reading, okay? So that's why you also never clamp around. If you've got 2 conductors, you don't ever clamp around both of them, because they have opposing magnetic fields, and those 2 magnetic fields will cancel each other out. So you could have 2 current-carrying conductors that are carrying current as something is running, clamp around both of them, and you're going to get 0 current. Very misleading and not the right way to do that, okay? So that's why we go around 1 conductor. So now it's time to see a conductor being measured for its current flow with an amp clamp, and that should wrap things up. Hope this has been helpful, and hope you enjoyed it. If you've got any questions, reach out. And again, we're going to cover all of these things when we come to lab. So you'll get your hands on it, and we'll go from there. Thanks a lot for watching. Okay, guys. this is our amp clamp demonstration, and what I'm going to do is open the jaws of this clamp and secure it around one of the conductors that's going to a heating element in our boil kettle. And what I'm going to do is I'm going to turn the boil kettle heating element switch on. It's going to pull a contactor in, and for those who don't know anything about contactors, that's fine. We're going to cover those in controls, but for right now, what will happen is the voltage will come through the top of the contactor, it will close, and then pass on through this conductor here that feeds the power to the heating element in the hot liquor tank. So as I turn it on, you'll see the numbers here on our amp clamp meter give us the amount of current flow that we will see that the heating element is actually pulling. So I'm going to be very quick about this because there's no water covering the element. So I'm just going to turn on for a brief second so you can see that, and I'm going to turn it right back off. So I'm going to turn the power to the contactors on and turn the heating elements on, and boom, we're sitting at about 28.5 amps. I'm going to quickly shut that off. So we were pulling 28.5 amps of current to the heating element. Now, you also remember that if you clamp two of the conductors in the same circuit, now both of these are going to the heating elements, but if we turn both of these on, it will null the magnetic fields between the two, and you get a zero or nearly zero current reading on our amp clamp. So we're going to do it very quickly again, and this time we're going to see how it negates the reading, and you get nothing. So you got about 0.1 amps, okay? And that is the result of having both of these conductors clamped. You always want to clamp one conductor with an amp clamp. But there